welcome to our Intel oneAPI webinar series. We're hosting this in partnership with Intel Software and Baincore. Thank you, Stephen, for joining us. I'll hand over to you in just a minute. Today's the first session. We're going to show you how to port Intel Parallel Studio code into Intel oneAPI. Obviously, if you do any questions, either put them into the chat bar or politely ask. My name is Daniel Payton, and I'm the Intel Software Licensing Specialist here at Grey Matter. A couple of you may have dealt with me before. Grey Matter is a software reseller and cloud services provider. Developers and technology-led companies are at the heart of Grey Matter, and everything that we do is designed to help them succeed and focus on what they do best. And as of last year, we're now part of the NASDAQ-listed Wayside Technology Group. And our cloud-certified experts are able to help customers migrate and optimize their projects in the cloud. We partner with over 400 software vendors covering a wide range of areas such as developer tools, platform security, productivity, and more. We work with big, well-known brands as well as niche specialists. Whatever our customers' needs, we'll source it. And we're really proud to be an Intel software reseller to support you with all your licensing needs and to be hosting the session for you today with Intel Software and Baincore. So I'll now pass you over to Stephen from Baincore, who will host the session today.
That's great. Thank you, Dan. So welcome, everyone. So let me introduce myself first. I'm Stephen Blair-Chappell. I'm an ex-Intel employee. So I worked with Intel for 18 years in the compiler department, working with support. And I'm now working for a company called Baincore, been with them, I think, 3 years now. And most of my work, well, if you don't mind the wrong maths, then 150% of my work is actually still for Intel. So that's where I'm spending most of my time. And increasingly, it's around the oneAPI project and so on. So with that, I'm going to start sharing my screen. And Dan, once I've started sharing, can you confirm you can still hear me? Because I'm using a couple of tricks here.
Yeah, not a problem.
Which, right. First of all, can you see and hear me? Can you see some slides and see me in the bottom right-hand corner?
I can see and hear, yep.
Okay, and I'm not too much out of sync. Okay, good. Oh, good.
No, it looks all good.
Right, okay. I won't bore you with the technical details, but I've got enough kit on here to launch a battleship, I think. So, okay. Right. So what we're doing now is looking at importing Parallel Studio code to Intel oneAPI. The agenda we'll look at a little bit what the API toolkits are. Now, I've already done one session previously, I think before Christmas. I don't know how many of you would have been on there, which I spoke in more detail about the content of the toolkits. Quite a big topic is about compilers, because the oneAPI toolkits comes with more compilers, and there's a certain amount of, or there could be confusion as to what compiler do I use. And so we'll have a little bit of a discussion around that. I then want to suggest a strategy that you could take in terms of migrating your Parallel Studio projects to using oneAPI. A few comments on supports, and then a few comments on the next few sessions. Now we're due to go for 90 minutes. Let's see how we go on in terms of speed. We may finish earlier. If it looks like we're going to go for the full 90, I'll probably put as a coffee break. Not that I can give you coffee, but we'll have a sort of a 5-minute break halfway through, give you a chance to stretch your legs and so on. So let's do that. So this presentation is on the assumption that you're already using Intel Parallel Studio. And the goal or the purpose of this session is to look at the practical steps. How do I move from Parallel Studio to oneAPI without breaking my great code and so on? So that's the focus. If you've not been using Parallel Studio, if you're not an Intel user of Intel software at the moment, the steps are still can be used, but you would probably be starting from either the Microsoft tools or on Linux on the GNU tools. Since the Parallel Studio tools, have got compilers that are compatible with the Microsoft and the GNU compilers, then much of what I'm doing translates directly also if you're coming directly from Microsoft or from sort of GNU rather than Parallel Studio. So let's talk about the toolkits. I think one of the questions that you're probably thinking right at the beginning, well, why do I want to migrate to oneAPI? And I think there are three main points to that. The first one is in order to use accelerators. I'll just go back to the previous slide for a minute. What you see on the left-hand side is when you're using Parallel Studio, you'd had your work running on Intel Xeon processors, or you may have been using another vendor's processors, but you would have been typically running on machines that have got CPUs inside them. With oneAPI, this offers the ability to run on other devices to accelerate parts of the code. So apart from being on a CPU, then you could be on a GPU, either an embedded one or one that's a distinct card, FPGA, and also other accelerators such as the Movidius Neural Compute Stick, for example. So one of the first reasons that people are going to oneAPI is in order to take advantage of this offload capability. And that's a very attractive reason for moving on to oneAPI. Let's go back to the slide that we were on. The second one is that as the Intel software moves forward, then the main development work is being focused on the tools that are within oneAPI. You'll see on the next slides that all the tools that are in Intel Parallel Studio are also in the oneAPI toolkits. Now, in terms of what's happening with the Parallel Studio is still being fully supported and maintained. But I think you'll find that new features, particularly on things like in the profiling tools, at the moment, most of that engineering effort, at least this is my observation, is happening within the toolkits rather than the Parallel Studio. The third thing is that with oneAPI, then there comes extensions or new language features, both in terms of the data parallel C++, which I'll talk about in a little moment, and also extended support for some of the new C++ and also Fortran language features that come up in the new standards. Well, I suppose the question you would ask is, well, will my code still build and run? And the answer is yes. And the strategy that we're looking at today hopefully will help you to have a fairly painless transition from the oneAPI, sorry, transition from Parallel Studio to oneAPI. The status of the oneAPI is that it's a released gold product, so it's going through all the usual QA and so on. But there's one product within the oneAPI toolkits that's still beta, and that's the new Fortran Compiler, again, which we'll talk about in a while. So in conclusion, can you use the oneAPI toolkits for your production code? And the answer is yes. Here's a slide showing the components that are in the original Parallel Studio. So this is the oneAPI toolkit for high performance computing, and that's the toolkit that we'll be mainly using today, because what I'm addressing is people that are already using Parallel Studio and then moving to oneAPI, and the Hpc Toolkit is the key one, I think. And you'll find in the oneAPI toolkit for HPC, then all the tools that you're already familiar with. So the Intel C++ compiler, with support for oneMP, the Fortran compilers, the Intel distribution of Python, various well-known libraries, obviously the MPI, the math kernel library, NKL, the data analytics library, and also the threading building blocks, and then the integrated performance primitives. Now, these libraries, if you're users of the Parallel Studio, then you will be familiar with these libraries, and they're the kind of the foundation to the performance that you get out of Parallel Studio. And along with the compilers and the libraries, then in Parallel Studio you had various profiling tools. So Inspector was for looking at memory and threading errors. Trace Analyzer Collector was looking at your MPI codes running across different nodes. There's a cluster checker to check the correctness of any cluster that you're doing, that it fits in with the recommendations that Intel have. And then there are a couple of profilers, the vTune profiler, it used to be called vTune Amplifier. That's a profile a little bit like, for instance, gprof or one of the other profilers, but capable of doing some very advanced architectural analysis apart from high-level user application analysis. And there's Intel Advisor, which gives recommendations both on threading and on vectorization. And then there's also an enhanced version of GDB. So those tools that are already in Parallel Studio moved and also extended their new versions, actually, when you look at them in oneAPI. Along with that, then you'll find this is the Hpc Toolkit, you'll find some new compilers and some new tools. And some of these I'll reference a little bit later on. The key one that you probably will notice is that the DPC++ is being mentioned a lot. So we have a compiler and a compatibility tool. So the Data Parallel C++ is a C++, with that, you can write code that can run on different accelerators. So you get different programs that are dealing with data to be sent off to an FPGA or GPU and so on. And that language is based on something called SYCL. We'll have a detailed discussion about that language in our next session, which is tomorrow. But the Data Parallel C++ is an important extension to oneAPI, and much of the training and examples come around that. But it may be you're not a C++ programmer, then you can see you've still got all the traditional programming approaches available, standard C, C++, and Fortran, and so on. Okay, so let's go on. This is the list of, I mentioned that the Hpc toolkit. There are a number of toolkits, which I will show you in the later slide. There's a base toolkit and there's a Hpc toolkit and a number of other. We're going to be using the base toolkit and the Hpc toolkit. You can see in the base toolkit, there are all the libraries that I mentioned previously. There's also support for FPGA and Data Parallel C++ and so on. And then the Hpc Toolkit. So these are all the new compilers, new libraries, and profiling tools that are being continually developed and extended. If you look at the Hpc Toolkit, in addition, you have the compilers that came with Parallel Studio. So this is why the high performance toolkit is also essential if you're moving from Parallel Studio to Intel oneAPI. So you see here we've got compilers, we've got new compilers, and we've got the old compilers. And this is one of the things I want to focus on in the next short while. Here's all the toolkits that are mentioned. As I say, there's the base toolkit. That's really the starting point. And then there's various add-ons. We're today going to be using the tools for Hpc. And next week, we'll be using the the Analytics Toolkit, and the week after that, we'll be using the OpenVNode Toolkit. Actually, correction, next week we won't be using the Analytics, we'll be using the base toolkit next week because we're looking at offloading in more detail. Oh, come on, too quick with my fingers. To get oneAPI, you can install it yourself. There are local installers, so you go down and just go to the link and download and install it to run on your Linux or Windows or Mac system. There are Docker containers available. There also can be installed through package manager. So for instance, on Linux, you can use apt-get or yum, depending on your package manager that you've got. And you can install all the tools without the need for buying anything. So they're available directly for download. But an important part of this is the way that the tools are supported, and I'll speak about support at the end of our session. What we're going to do today is that we're going to use something called the Intel Dev Cloud. So this is something that you can register for and get free access. I think it's for 90 days, or is it 120 days? I get mixed up. But anyway, for quite a number of a long session, you can register to use the Dev Cloud, and it has all the tool features already to for you to experiment with them. And that's something we'll be using today. So if you go on to this particular site, so the website there, then you can get straight onto there. It's got examples, all the tools are already installed, there's support for Jupyter Notebooks and also Visual Studio Code. Very easy way of getting on straight away. One thing I would say is that if you're planning to use the Dev Cloud, then don't put it as part of your strategic path in your work, because there are occasions when the Dev Cloud just isn't available. Like for instance, Thursday and Friday of this week, or in the afternoon, they're doing an update of the logging system, and so on. So it's a nice thing to have, very beneficial, but don't make it to be the key component in your migration strategy. Use it, yes, but don't depend on it as being the only way of migrating your code. Here's how the Dev Cloud works. So the way that it works is that there is a login node, and when you go into the login node, you then create a number of scripts to ask the compute nodes to do some compilation and profiling and so on. And it's a non-interactive mode normally. So and there are guidelines and so on how to do that when you log into the Dev Cloud. But there's a second way of being able to use the Dev Cloud. So what we're going to be doing is, rather than logging in onto into a terminal and onto the login node, what we're going to do is we're going to use notebooks. So we're going to use Jupyter Notebooks as it's more convenient. When you use a Jupyter Notebook, you get placed straight onto a compute node. Now there is the possibility that somebody else may also be sharing some of the resources, although you won't see them. So for performance, the notebooks can sometimes be underperforming if you've got someone else doing some work on the same compute node at the time. So say in the diagram, normally for proper sort of development work, you'd connect via SSH and you'd submit jobs to a queue, and they would then be dispatched to whatever kind of hardware that you're looking to use. And the Dev Cloud has got support for CPUs, GPUs, FPGAs, and new up and coming architectures as well. Okay, if you go on that website there, you can get free access. So this is the two ways. What we're going to do is we're going to use the Jupyter Notebook. Okay, so what we're going to do now is let's actually do that. So I'm going to switch to a different machine. Let's see, this should all work wonderfully. Okay, good. Mouse as well, even better. Right, let's just delete these notifications. So what I've got here is I've already, when you register for the dev cloud, then you'll send to URL, which has got all your login details. And this is the method I'm going to use. I'm just going to, so I'm operating on a local machine using a browser. And I mean, I could have used a terminal and SSH'd into the dev cloud, but I'm choosing to go into the via the web browser. And then when I go on to the getting started, just wait for it to load. Within there's a set of samples that you can load and also training modules. And these are very useful for getting to know not only about the dev cloud, but also about oneAPI. What I'm going to do is I'm going to go straight down to the bottom here and launch Jupyter Lab. So that starts up a Jupyter server. Once that's working, then I will get direct access to a compute node on the dev cloud. Just wait for that to start up. Okay, and on the dev cloud, there are instructions on how to use the dev cloud, more detailed explanation of the structure. So, but what we're going to do, since we're actually on a Jupyter notebook, then we're not on a login node, we're already on a compute node. So if you see on this diagram here, on the right-hand side, you see notebooks are already sitting on compute nodes. And within the notebooks, you can either use QSub to still submit to the job queue, or alternatively, you can run code directly from the notebook. And I'm going to run code directly from the notebook rather than submit job queues or something to the job queue. So let's have a look. So let's open up a terminal. So let's get this. So what I'm going to do first of all is just to see what kind of CPU that I've got. So if I use ls CPU, okay, so we've got Xeon Gold, okay, and what you see here is I've got 24 cores, and it looks like it's a 2-socket system. Yeah, 2-socket system there. And then if we go down, let me just move myself somewhere else. Okay, so if you look down here, you can then see the kind of instructions that the CPU will support. And you can see here that this compute node that we're on has got the AVX512 support and so on. Okay, so that's the system that we're on. Let me just go back to the slides for a minute now. And let's put myself back over there. So when you look in the installation of oneAPI, although there are distinct toolkits, when you look at the installation, the toolkits are not as you would expect. Let me turn this off for it. And so there's a oneAPI root folder, and then there will be subfolders for each of the components. so compilers, libraries, profiles, and so on. So they won't be collected together as a base toolkit, Hpc Toolkit, IoT Toolkit. Rather, they'll be separate components in a very sort of flat structure at the top level. And then within each of those subfolders, there'll be a folder for each of the version with a soft link called latest, pointing to the latest version that you've got. If you're on a system, Linux system, where you're using modules, then modules are also supported in oneAPI as well. So let's have a look how that looks here. So first of all, let's have a look where one of the tools are. Okay, so what I'm going to do is just go to the location of the tools. Let's do it from there, I think. In fact, let's do it from there. Just clear that. So what I've got here is the different versions that have been put on the dev cloud. Let's go into the 2021, which is the latest release. And what you see under here is that we've got a folder for oneAPI. Let's have a look. So let's just do that command again. Just make sure I'm going in the right folder. Yeah, so I need to go into Intel oneAPI. Okay. And what you see here is that there are the folders for the different tools. So we've got the compilers, got the trace analyzer collector, for instance. We've got the different libraries, the integrated performance primitives. We've got various, we've got the sort of ray tracing and rendering tools. So we've got Osprey, Embrace. And these are all from the different toolkits. So as I said, so whilst when you download a kit, then you get installed the appropriate tools for that kit. They're a very flat structure. For those that are Windows users, you'll see a very similar structure. So I'm actually on outside this browser, I'm on a Windows machine. I mean, I'm logged in on the Jupyter Notebook into a Linux machine, but let's just go to my Windows machine. So I've also got oneAPI installed here. There's a particular script that you have to call. Let's do that. So this is the script for the Windows tools, and I've set the path up, and you see that again the tools are again mentioned. And if you were to look in the default folder, it's not. I can't remember where it's now installed. It doesn't really matter. It's not. I was going to go on the Linux path. It's not. But so anyway, but you can see here that all the different tools are again available on Windows, the same as on Linux. Okay, so let's go back to the slides for a second. Okay, so you've seen the modules. Now, one of the important points is about compilers. What compiler should I use? And the oneAPI comes with lots of compilers. And here's some comments that I found. So it says, someone writing on the chat said, I recently installed the oneAPI on my laptop, see how it works. Everything's going nicely, and I can compile some projects with ICX and DPC++. But in the server, I've only got ICC and ICPC. Okay, so he suddenly sees that he's got both the classic compilers, the compilers that came with Parallel Studio, but also he's got the new compilers. And the question is which compilers should we use? So that's one comment. And then the second comment that he makes is that he's managed to download all the tools and he's realized he doesn't have to pay for them, which is also true. But if you want to have professional support with the tools, then there's a paid service you can subscribe to. So, compilers. In the oneAPI, there are two categories of compilers, and you saw it when we looked at the content of the Hpc Toolkit. There's the classic compilers, so those that are in Parallel Studio. So there's ICC and ICPC and iFort. So there's C, C++, and Fortran compilers. Those are the same as in Parallel Studio, but you're not able to do any offloading to accelerated devices. The new compilers that come with oneAPI are LLVM based, and those have got a subtly different name. They've got X at the end in the case of the C and the Fortran compilers, and then there's a completely new compiler, the Data Parallel C++ compiler. The thing about these compilers, all six of them, is that they're all objects, they're all binary compatible. So you can mix, you could build some of your code using the classic compiler, you could build some code using the new LLVM compilers, and you can link them together. And it's this particular feature that's very helpful when porting from Parallel Studio to oneAPI. So yeah, we got that. So some words about the compilers. First, the C compilers. On the diagram on the right, there are two sort of columns, as it were. The left-hand column is the classic compiler, the compiler that you would find with Parallel Studio. It's called ICC. And on the right-hand side, there is the new compiler, ICX. They're both C and C++ compilers. But the difference is that the ICX compiler is LLVM based. So it uses Clang as a front end. And let me just close the door because there's a phone going off in the distance. Hold on. Right. Good. Got silence now. So this uses LLVM. So the front end takes the language that you've written, it converts it to LLVM intermediate representation, and then there's a new backend which is LLVM based, and that most of the work on that compiler is new. So you'll find that everything is, well, it's closely aligned to the Clang LLVM community, and it's all the things that you see in the LLVM compilers you see here as well. If you look at the left-hand column, so this is the classic compiler, then this is using, so this is the compiler that's now coming with oneAPI, but it's the classic compiler, not the LLVM one. Then it's using the same front end that was being used previously in Parallel Studio. So it's got its front end, it changes, so it uses an intermediate representation called IL0. The back end is also using IL0 and it's ICC. So it's the two compilers are completely different. One is not a plug and play replacement for the other. So with the LLVM compiler, that's following very closely the standards in terms of what LLVM is doing and the new C++ standards. But there are differences in the way the two work. So, for example, there are various advanced features and tools for looking and analyzing what the compiler was doing with the classic compiler, a tool called Brutus. Don't worry if you don't know what it is, or the compiler optimization reports and so on. They're in the classic compiler, but they're not available in the LLVM compiler, although Intel are doing some work to improve some of that. But the two compilers do work differently and have different front ends. So even handling the language that you write is different, the kind of error message that you give and so on. If you look at the Fortran compiler, the situation is slightly different. So on the left-hand side, we've got the classic compiler, the one that was originally with Parallel Studio. And on the right-hand side, we've got the new LLVM compiler. The difference here compared to the C compiler is the front end is the same front end for both the classic and the LLVM compiler. And what this means is that taking your Fortran code that you've written in Parallel Studio, for example, and then building that with the new LLVM compiler, the front end will recognize all your code without any problems. There are no differences in implementation of the language parsing at the front end. And if you remember on the previous slide, the C compiler had different front ends, and that could bring you issues around porting. So if you've got language on your C compiler that maybe isn't quite tight to the standard, LLVM will pick it up. On the Fortran front end compiler, the front end is the same front end. It shares the same code. And so Fortran users have got a much easier task of porting their Fortran codes to the new compiler. However, the Fortran compiler, so now looking at the right-hand side, this one, although it's got the same front end, the middle end and back end is still being developed. So not everything that is in the language is necessarily yet implemented. And so the recommendation is for most Fortran work this year, when you move to Parallels, to move to oneAPI, use the classic compiler, not the LLVM one. That's the recommendation. And as I said earlier on, that compiler is still in beta. The Fortran LLVM compiler is still considered as beta. The way that the comparison of the Parallel Studio and oneAPI, remember the whole discussion today is about porting from one to the other. Parallel Studio, you've got when you call the compiler, you have various drivers, ICC, ICPC, and iFort. Its version is 19.1, so that's the last version you've got of Parallel Studio. If you look at the oneAPI based toolkit and the Hpc Toolkit, then the classic compilers are now a couple of versions up, so they're version 2021.1 as opposed to 19.1. So there have been some, on the classic compiler side, there are some further enhancements and maybe the odd bug fix and so on, which have been implemented. So one reason that some people move to oneAPI but still use the classic compiler is to keep track of using the latest compilers. Okay, I've got an alarm coming up which says 43. I was going to have a coffee break at this point. So I think what we'll do is we're going to have a 5-minute coffee break. Okay, so what we're going to do now is to move on to the demonstrating using the tools and porting some code. So let me show you just 3 more slides on the compiler. Let's move back to there. Yeah. So if you look at the compiler, the different versions, if you call the different the classic and also the LLVM compiler, you'll see that they're different versions. You see that they're all 21. Let me just get this there again. It's 2021.1.2. The only one that's different, if you look at the bottom, the LLVM version of the Fortran compiler is still beta. And for that reason, we recommend that you're very conservative about using that in production code. In fact, you shouldn't really use it for your experiments at the moment. Stick to the classic compiler when using oneAPI. The drivers, so when you call a compiler, the drivers, the compiler isn't called directly. There's a driver that handles things like the different options that you've done and so on. And if we look here, then the classic compiler, so that's the left three, no, it's not, sorry, it's ICC, iFort, and those are the classic compilers, so the first and the third one. Then they called the compiler itself, which is called MPC-com and Fortcom. You normally wouldn't call those, you'd call the driver, and the driver in turn would call the compiler. In the new compilers, the LLVM-based compilers, then the drivers will still recognize the options that you're using with the classic compiler. So and what they do is that they will map the best option. So if you've got a series of options, then using ICC and you decide to use ICX, you can use the same command line options. However, some options may not be supported. So what ICX does is it tries to map your options to the best option available. And if not, there are some strategies for dealing with options that are not supported. So let's have a look at the migrating from Parallel Studio to oneAPI. So we know what's available in the two scenarios. We know that there are different compilers, and we're going to take advantage of the fact that the compilers produce binary compatible objects. And that's the key to a very successful and easy migration path. There are three strategies that you could take in migration, and we'll go on to the dev cloud in a moment and see these in action. The first one is you simply take all your code that was in Parallel Studio, you install oneAPI, but you continue to use the classic compilers. So in this case, for C code, you'd still continue to call ICC. For Fortran, you'd continue to call iFort. And as I've said already, for Fortran, that's the recommended route this year anyway. Consider the LLVM version of the compiler to be experimental. So that's a very safe, that's the safe option. The second one is to begin to use the new compiler. I say the safe option, the previous one, that's the one where there's no change apart from installing the tools maybe. The second one is where you begin to use the new compilers. And say one of the reasons, I said at the beginning, one of the reasons you might want to use the new compilers is either for new language features, or it could be that you want to accelerate some of your code. And that will be some of the reasons that you'd want to move. So in that case, for the C compiler, you'd just compile things with ICX. And then with the compilers, the Fortran code, you could use IFX, but there's some limitations with that, which I'll talk about on the next couple of slides. The third strategy you could take is have a hybrid one. And with a hybrid one, you'd get some of your code that's not vectorized. So it's not relying on the classic vectorization, the vectorization facilities of the classic compiler. Maybe your code isn't vectorized, you've got mainly integer code and so on. Then you could put that code and use the new compiler. But if you've got code which is highly vectorized, so for example, at the top here, I've got the top C code is going to the new LLVM compiler, but the next chunk of code, I put vec there to indicate it's highly vectorized. You might choose to continue to use the classic compiler because of the vectorization efficiency that you're used to in ICC. And with Fortran, you could do the same thing, but my comment again is to say is consider that the LLVM version of the compiler is experimental. When you're beginning to look at offloading onto other devices, then you would have to use the new version, so the LLVM version of the compilers. As I said earlier, the classic compilers don't support offloading. That's a topic for next week. When you're looking at ICC and moving to using the new compiler, issues to look for are compiler options, Pragmas, and compiler intrinsics. If you're on Fortran, then the issues to consider is the status of the compiler. Not all the language features are supported. If your code's got features that just Fortran 2003, it'll probably work fine on the new compiler. If you've got some more exotic features from 2018, for instance, then it's likely that the internals are not yet implemented in the LLVM Fortran version. Here are the migration steps that you could do, and we're going to do those in a second on DevCloud. You start off, if you're a Fortran code, check what language features are there. The second step would be to check if there are any Pragmas in your code, because the Pragmas won't be the same if you're moving to the new compilers. Third thing is to check the command line options. As I said earlier, the options may have changed. Next is to do a smoke test with a new compiler. The fourth step would be to decide which of your codes you're really going to migrate. And then the fifth step is migrate itself. What I'm going to do now is to go onto the DevCloud, and we're going to just do some experiments. So back onto the DevCloud here. So let's see where we are. So I've got some examples that I created earlier, which I'm just going to go to. Tell you what's, why don't we close that more space? Right. I'll quickly look at a Fortran example. So this Fortran example has got a piece of code. In fact, let me just show you the code as quickly. I think I might have it. Yeah, I've already got it open here. So it's a piece of Fortran code that uses co-arrays. So co-arrays came in the, I think, 2018 version of the Fortran standard. So this isn't yet supported in the new compilers. The way that it works is that the runtime system creates a set of images, and then the images are the same number of images creators that there is hardware support for hardware threads. So so if you're running on a 4-core system and it's got the hyperthreading enabled, then it would generate 8 images, for instance, and those would all run in parallel. So this is just a piece of code. It's just hello world really on that. So let's see how we get on with building and running that. So sorry, wrong one. Back here, back to our. Let's just clear the screen. So my first example is just running with the classic compiler. So let's do call that script, and it's calling the compiler, no problem at all. So and there'll be a.out. Let's just run it. And you remember we discovered earlier on that we've got 24 cores on this, and you can see that there are 24 different messages here. Okay, so it's run in parallel 24 times. Let's do that again. The second script is, this is now trying to build the compiler using the, build the code using the new version of the compiler, so the Fortran LLVM version. If I run that, what we have here is, well, it's been kind, it's told us that the co-array is not supported, but it doesn't build an output because we're using a feature that's not yet implemented. Now, the way to check what features are okay is that you can check to see what standard your code is. So let me show you what I mean. There's a compiler option, which I've got in the third script. So there's this stand option. So I'm now calling the classic compiler. So I'm moving back to the classic compiler, but I'm asking the compiler, warn me about anything that's above the standard of Fortran 2003. If you remember, I told you that the new LLVM compiler doesn't support all the new standards. So, but Fortran 2003 is safe. So if you're experimenting with Fortran code, wanting to use IFX, maybe because you want to be offloading, then first thing to do is to do this check. Build it with the classic with this option. So let's do that. And what you'll see, I keep getting this wrong. Okay, so why is that? Oh yeah, so my terminal's running a bit slow here for some reason. Everything's running extremely slow. So remember, I'm connected to the dev cloud. Okay, the dev cloud has just slowed down to a treacle. Okay, right. Well, we'll do our best. So okay, well, if it all runs at this speed, we're going to be okay. And here what you see is we get warnings of the 4000, 2000, sorry, the Fortran, anything that's above 4000, 2003 standard, you get a warning saying this isn't in the standard. So if you're experimenting with using IFX, you're porting code from Parallel Studio, iFort, going on to oneAPI, wants to use IFX, this is the first step that you should do. The next step would be to, excuse me, would be to migrate the command line options. Okay. Well, no, it wouldn't be. It would be to do the. Let me go back to my slides. Then we're not out of sequence. What we've done now is with the step 0, we checked with the iFort. Most people have. Only Fortran programmers are interested in that. The next thing is now to check Pragmas. The examples I'm going to do here, we're going to use a C example. So, and there's an option to check if there are any Pragmas that are not known. So we go back to our example here. I should go to here. I'm now going to go to an example that's got the vectorization examples, and there are a load of scripts. So what we're going to do is just going to build the, let me just show you the file. What this is doing is calling a make file, and I'm passing some flags in, and the make file inside calls whichever compiler what ICC is set to, and so on. So I'm just going to build that. So this is using the classic compiler. Remember, the goal here is that we're wanting to move towards using the new compiler. We're going through some steps that you would do in your projects. So the first one we built it, we'll just make sure that it runs. So ICC AVX. So this at the moment is built using AVX2. I could have put AVX512, but I didn't. This is just running a piece of code that runs 6 times and everything's running fine. The thing to remember is, in fact, let's write this here. What I'm going to do is just flip you onto a different screen for a minute. So that was the ICC with AVX2. Just remind myself what so it was, let's say 1.51 seconds. I'm just looking at the wall time, okay? Now if we go back to here, what we're then going to do is, the first step I said was to check the Pragmas. So I've got a set of scripts here that I've put. So if I cap the O2, then what we've got here is that there's an extra option. So what we're doing now is we're trying to discover whether there are any pragmas that are not supported in the code when you use the LLVM version of the compiler. So what I'm passing in now is the compiler is now going to be ICX, and I'm saying, warn me if there are any in this particular option there that you should do. What I'm doing here is I'm just compiling a particular, the file that I know has got some pragmas that aren't supported. I've chosen that on purpose. So let's run that code as well. So that would be O2. Oh, it's gone very slow. And there you see that the new compiler has brought a warning, Pragma unknown. Now, I'm actually using a very old Pragma, SimD. If you were writing code, even for Parallel Studio, you should really be using the OpenMP version of the SimD Pragma, Pragma OMP SimD, rather than this one, which is quite an old one. But you see the point is, get your code, run that. The next step, let's go back to our slides. So we've done that, is to look at the command line options. And with the compiler, and I'm looking at the ICX, remember they have different front ends. The LLVM compiler, the C compiler has got a different front end to the ICC compiler. So some of the commands may not be supported. There are two types. There'll be ones that are never going to be implemented and the ones that are not yet implemented. And the compiler will give you an up-to-date list of those if you want to. So if you call ICX with this Q next-gen diag, it'll give you a list of options and their status. So let's go back to our, so let me show you the, so I'm now going to call the ICX. This is just a, I'm not calling any file, not compiling anything. This is an information thing. So let's call that and see what information it gives. And what you see here is that there's a list of options, two categories. I'm scrolling upwards. There are a lot of them. So I'm scrolling up, scrolling up. So these are the options that are not going to be supported. These are being removed. So these will not appear in the new compiler. And then the other one, then we go up here. Let's go, still scrolling up a long list. And these are options that will be supported. Now, when it says to be supported, it means it's not yet supported, but is going to be in the future. Yeah, so you can see there's quite a few options that are not yet mapped across to the new compiler, but the intention is that they will. So if you're using these options, then you're going to have to find a strategy to not use these. If you use a compiler option that's already implemented in the new compiler, the compiler driver will just replace it with its new option. Okay, back to my slides for another second. So we've done the check what the up-to-date list. You might need to look at that. The next thing to do is test whether your code still runs with the new compiler and look at the wall clock time. So let's just quickly do that. Let's clear that. So what I'm going to do now is to run the build, everything being built with the new compiler. Okay, so this in fact is O2. No, it's not, it's O3, isn't it? So this is calling the compiler. Let's see, the output is slightly different, it's got a different name. So if we do ls, so now we've got a ICX AVX. So notice the name's just different. So let's just call that quickly. If you notice now, the excuse me, the elapsed time is about 1.6. Let's just write that down. So ICX, that's still AVX2, and it's about 1.6 or 1.61 or something, wasn't it? So you can see that the wall clocks got slower. Let's go back to there. Now, what you could do, if you wanted to, was to do some analysis of why it's different at that point and use the different tools to do an analysis. But that was just sort of a smoke test, make sure everything builds and runs with a new compiler. What we're trying to do is to identify what candidates should be migrated. And what we'll do here is to go on to our just go into the slides again for 1 second. So you build with a new compiler, which is what we've done. Compare with the wall clock. You could optionally analyze it. The next step, step 4, is to look at the migration candidates. Now, the recommendation, which what I mentioned earlier on, is that use the classic compilers for anything that's heavily vectorized or anything that runs slower with ICX. And you use ICX for hotspots that run at the same speed as the classic. And or you might eventually then also use ICX for code that you're going to offload, but we'll discuss that next week. So here we've got code that we're going to, so our goal now is, we know that the building everything on ICX runs slower. What we want to do is to find the bit that's running slower and keep that with the classic compiler. So let's go back to our, just close this door again. So what we've got here is that with your application, you could do a series of analysis runs with different tools, with vTune, something called application performance snapshot, and so on. What I'm going to do is quickly run the application performance snapshot. And all it is you code APS and then the executable. I'm going to run this on the original build. So this is the one that was run with the classic compiler. But what I'm looking at is that I'm trying to find if there's any code which is vectorized, because in my porting or migration strategy, I'm thinking any code that's highly vectorized, I want to stay with the classic, because that's probably the area where I might lose performance if I use the new compiler. So let's run that. That's 05. So what this does is that it's the application performance snapshot is a standalone utility. It's actually also packaged with vTune as well. It runs your application, and then it does an analysis on how your memory is being used, and also how the vectorization is and how the CPU, the multi-core aspect is. It gives you a textual output, but it also gives you HTML version. And what I want to do is to go on the HTML version. I've already downloaded it earlier on, so I'll cheat and let's see if we can just find that. So we go on to downloads. This is an example. It'll have a different name now, the results will be the same. The application performance snapshot is, remember I ran this actually with a classic build. The question I'm trying to answer is, I'm trying to identify migration candidates. Which things shouldn't I move onto the new compiler? Which things should I stay with the classic? And the areas I'm looking for are areas where there's a lot of vectorization. And if you look here in this column, that we have vectorization being reported here. We've got things called packed instructions and so on. Now, this is likely that the efficiency of this code is down to the vectorizer in the classic compiler. You may get the same performance in the new compiler, but if you've got highly vectorized code, the recommendation is to go with this method. I'm going to go onto the my notepad, back onto just showing you a diagram. So we've got a piece of code which was originally built with Intel Parallel Studio, and within it there might be some code that's vectorized, but the rest isn't particularly optimized. This is our kind of sweet spot, our hot spot of code that we've worked for years on, got it running perfectly well. The way that we get our optimization is that on your system, so that this is a CPU node, you might have two nodes. In our case, we haven't. You could have two sockets, and within each socket, there is a CPU, and each of those CPUs will have lots of cores. In our case, I think we had 24. And then within each of these cores, there are a number of execution units. And typically on a Xeon, the execution units, there's 6 or 8 execution units. And these are dedicated. Half of them will be related to doing sort of SIMD and other operations. And the other half will be to do with I/O, reading and storing. Now, when it comes to the SIMD operations, the execution units have some very, excuse me, some very wide registers. And the idea is that the more than one data item is put in at once. So this could be, in our case, we're using AVX2, so we're using 256-bit wide registers. If we'd have chosen AVX512, that'd have been twice the size. We have data put into each of these, and we have special instructions which enable a calculation to be applied to both data items in one instruction cycle. So this is where we have the vectorization. Now, what we're doing with the classic compiler is there's a huge amount of work done by the compiler in taking advantage of this. So the recommendation is that for the vectorized code, stick with ICC. So this part will be built with ICC, but it might be that the rest of the code isn't vectorized, especially, it doesn't, but it's just sort of generally optimized. Then these bits of code you would build using ICX, for example. And even at a later stage, you might want to take advantage of running some of this code onto a embedded HD graphics or a GPU or an FPGA. So you see the reasons, keeping ICC for the highly vectorized tuned code, but the rest of the code you would use ICX, giving you the possibility of even offloading. And this part we'll look at next week. Okay, so what I'm now going to do is to go back to the results. Let's have a look. So in our case, the application performance snapshot showed we'd got some vectorized code, and what we'll do in the next two steps is to build that part of the code using ICC, but the remainder of it using the LLVM version of the compiler. So let's go back to our Jupyter Lab, which is here. Let's just do a Control-L. So what I've got here is the example. You could continue and do some other reports, use vTune, you could use compiler reports, you can use Intel Advisor to look at the vectorization. Those could be other sets of analysis you might do at that stage. But then you'd go to the stage of getting a hybrid build. And what you're trying to do is get the same performance as when you have the classic, when you're with Parallel Studio. So we've spotted that our code runs slower. It's got parts which are vectorized. And so what I've done with the hybrid version, That's 09. So what I've done here is that I've taken the part that's vectorized and I'm sticking with the classic, and then I'm using the LLVM compiler to compile the other source codes. And also in this case, the LLVM compiler will be the linker, and you must do that if you're mixing. You must use the LLVM as a linker, to get success. So let's run that. That was 09. So building it, give me some warnings. So that's the SIMD warning. If we look now, we've got the hybrid. So let's run the hybrid. Okay, right. Today it hasn't run the way I expected, but let's look at the result. I think there must be somebody else also on the same compute node. You know, when I said it started running slowly earlier on when I was typing, it's probably because someone else is running a Jupyter notebook on the same compute node. So let's go back to here. It was 1.51 and then it was 1.61, the wall clock time. If you have a look, we're still at 1.68. I was expecting that to go down. Okay, in my previous experiments, when I do it locally, I end up, it's speeding up. So still being slower than the classic, but faster than when it's just built using the LLVM. But those are the steps that you would do. So what I'm going to do now is go back to my slides as we move towards the end of our time. Let's go back to here. Okay, so we'd identified the candidates by looking at choosing the, as I said, the vectorized stuff to stay with the classic compiler, the other parts going with the LLVM. And the final step would be to migrate. So you'd modify your build system so that you take into account your decisions, run it and compare things. There are some other things that might affect what you're doing. The diagnostic messages in the LLVM compilers are quite different. So if you've got a sort of a QA system that passes the messages from the compiler, you'll need to take that into account. The second thing is that the linking into procedural optimization and profile guided optimization are using different techniques in LLVM, and they're relying on the implementation in LLVM. So for example, if you're familiar with this technique with Parallel Studio, you'd be using the separate linkers, for instance. You wouldn't use those linkers. You must use the native linker when you're using the LLVM compilers, if you're using IPO and PGO, for instance. The third thing is that I mentioned earlier that the intrinsics were supported in the old and the new, but LLVM is much stricter at parsing any code. And with the classic compiler, you can get away with having wrong types for your arguments. But with the LLVM, it does type checking. So you must make sure you've got the right types when you're passing values into intrinsics. And also you must use the -m option to bring the right set of values. So if you're using intrinsics that are using AVX2, intrinsic instructions, you must use -m AVX2, for example. If you're doing lots of intrinsics and inlining, you should consider using the multi-versioning. In the classic version of the compiler, there's a number of different ways of getting your code to run on different versions of hardware. So on AVX and SSC, there's vectorization, but some people also use intrinsics and put their own SSE instructions depending on whether they're running on AVX or AVX2 or just an SSE. If you want to do something similar using the new compiler, then the recommendation is to use the GCC style of multi-versioning. And here's an example. We've got the function at the bottom, main. We've called it, and then we've written functions that the names are our names, called dispatch func. I've created 2 versions, and you use the attribute target to say this function is compiled to run on this kind of hardware, on AVX2, for instance, or on the default, which is SSE2, I think. So here, at runtime, when you call dispatch func, if I was running on my laptop, it would run on the AVX2. And inside those functions, you could put your own SSE or your own intrinsics. And I know some people specifically use that to tightly control some of their hand-optimized vectorized code. So that's the way that you do it with the new compiler. Okay, we're moving towards the end of our session. Just got 2 or 3 more slides of information. If you're working on using MPI and you want to use the new compilers, then it's just a case of passing the option with the -cc option. So if you look, for instance, on the first entry in this table, the C option, look on the right-hand side, an example. So calling the MPI CC, and we pass in the -cc equals ICX, and that causes the LLVM version of the compiler to be used in the MPI builds. Documentation, there's 4 lots of documentation here that's useful. One's on the LLVM version of the C compiler. The second one is the classic version of the C compiler. The third one is both the Fortran and also the classic and the LLVM version are merged together for the Fortran because it's the same front end. So the documentation will be very similar. At the top of this list, we put a porting guide, which will give you more hints on moving from the classic compiler or from using the old compiler onto using the latest compilers. On support, there's technical support available from Intel, and the resellers got information on that. And most people developing professional commercial applications will go with this support. There is a community support available, which is free, but it's not private, and it's not guaranteed to be accurate because it's just the community replying with what they think is the correct answer. And then the third thing is Baincore have got an advisory desk that's going to be available soon. That information is for the future. Okay, so to sum up with, migrating from Parallel Studio to oneAPI should be painless. You've got 2 versions of the compiler, both the classic and LLVM. Use the classic for vectorized code or code that's involved in benchmarking. Use the classic for more Fortran code. Consider using the LLVM compilers for offloading to accelerators.